Welcome again, everyone. In this sequence of lectures, we're going to talk about combinatorics, and which basically are somewhat more advanced ways of counting structures, and we'll start talking about permutations. Right. So a permutation is an ordering of a set of objects, and we are interested in counting the number of permutations of n objects. And the objects can, of course, be anything. It won't matter to us what they are. So they could be, for example, aardvarks or unicorns or dinosaurs. But to make the talk as exciting as possible, we'll, of course, use letters. So here we'll first look at some small cases. We'll look at what happens when we have a small number of letters. Okay, so here, if we have a single letter, let's just say call it A, there's only one way to arrange that, so that's number of permutations is 1. If we have two letters, for example, A and B, then we can arrange them as AB or BA, and there are two ways to do that. If we have three letters, for example, ABC, we can arrange them as ABC, ACB, BAC, and so on up to CBA, and one can see that these are all the ways to arrange the three letters, so the total number here is 2, 4, 6. Okay, and we're interested in counting this number as a function of the number of objects that we have, right? So, so let's see what happens when we have two objects, A and B. Then we can start with A or B. So we have two ways to start the sequence, two choices. But once we started with A, then the next object must be B. And if we start with B, the next object must be A. So after each choice that we have, each of the two choices that we start with, we have a single choice to continue. So if we view it as trees, which as we said we can always do, we can always view any collection of sequences as trees, then first option could be A and then B. And if we have A, we can only continue with B. If we start with B, we can only continue with A. And how many different sequences are there? It's the total number of paths or total number of leaves in this tree. And we have two branches at the beginning and then one branch later on. So the total number is 2 times 1, which is 2. Okay. If we look at three objects, A, B, C, for example, then as we mentioned, these are all possible permutations of ABC, all possible ways to arrange those three letters. And and we can do it with using three choices at the beginning, two choices. So for the first letter, we can choose A, B, C, which is three choices. Once we choose a letter as the first one, for example, A, we can follow it with one of two different letters because we've used one out of the three. And then once we chose two different letters like A and B, there's only one way to continue it. So there's only one choice for the third letter. And if we view it as trees, then we have three options for the first letter, A, B, C. Once we chose the first letter, we can branch in two ways, either B or C, if the first one was A, and we have one branch, one possibility for the third letter, and we can see that there are three branches at the beginning corresponding to the three possibilities, and then the second level we have two branches for each node because we have used one letter, and we can use one of the remaining two to continue. And once we get to the next level here, then we've used two letters, and there's only one branch because we can only continue each of the sequence in one way. So the total number of sequences, or the total number of leaves here, is going to be 3 times 2 times 1. Again, by the product rule, is 6. So we're using the product rule again. And therefore, the number of permutations in general of n objects is going to be n possibilities for us to write the first symbol times n minus 1. To write the second one, or n branches here, times n minus 1, and so on, n minus 2 up to 2 times 1. And this is denoted by n factorial. And it's called n factorial. Okay? And to do that, as we said, we use the product rule. So now, for n bigger than or equal to 1, as we said, n factorial, which is the number of permutation of n objects, is n times n minus 1, and so on, times 2 times 1. But what is 0 factorial? Because we cannot write n times n minus 1 up to 1 if we start with 0. So what is the meaning of 0 factorial? So the question is, how many ways can you permute 0 objects? And I think maybe the difficulty we might have in visualizing it is because we're trying to see something that does not exist. Because, for example, if we have two symbols, A and B, then the possible permutations are AB and BA. If we have just A, the permutations are just A. But if we have nothing, no elements, how many ways can you arrange that? Can you arrange it in 0 ways, or 1 way, or more? And I think that the difficulty is exactly because we cannot visualize the empty set. And the reason is because we stripped it out of all content that we used to have. So if you remember, we're trying to visualize in some sense a void. But if you remember, we said that sequences were actually an abbreviation for tuples. So, for example, for AB, we had the tuple A, comma B. We omitted the comma, and we omitted the parentheses, and we're just left with AB. So once we do that, when we get to the empty set, we have nothing to see. But if we kept either all the commas or even just the parentheses, then we'll be in better shape. So here we have AB and BA. Those are those sequences where we're keeping the parentheses, but maybe dropping the commas in between or not, that doesn't matter. And then if we have a single element, then we'll have just this parenthesis and A. This is the one tuple consisting of A, and these are the two tuples, A, B, and BA. And we're asking how many tuples can we have that have A and B in some order. How many tuples we can have that have A. And if we are looking at the empty set, then this is the only tuple that we'll have. It's just the tuple that contains nothing. Okay, and clearly there's exactly one such tuple. There's just this tuple, just like here there's one tuple. So therefore, 0 factorial number of these tuples is exactly 1. Right? And this, by the way, is the exact same reason why we define 2 to the 0 to be 1. It's exactly the same. Here we're multiplying decreasing values, whereas in the other case we're multiplying the same value, but 0 times, we would still get 1. Right. So in this day and age, people talk a lot about what is a fact and what is an alternative fact. So we want to discuss an alternative factorial view. So so far we counted the number of ways of arranging things, or n factorial. We counted it by writing the terms from left to right. So we wrote them left to right, and we counted how many elements, how many different objects we can put in the leftmost location, how many elements we can write in the second location, and so on. So we got n for the first one times n minus 1 times n minus 2, which is a little odd because the numbers decreased instead of increasing. And what we'd like to do now is look at an alternative way of counting the number of ways to arrange objects, or count n factorial, by instead of looking from left to right and counting how many different elements we can put in each location, we want to write the elements from smallest to largest and seeing how many locations we can write them in. So if we do that, so let's call the elements now, for example, 1, 2, 3, up to n. So for the first element, we put the first object, there's only one location we can put it. Wherever it is, it's just one location. Let's say we call it 1, we put it in this location. Okay. Now, once we do that, then the second element, we have two possible locations. We can put it to the left of the first one or to the right of the first one. So we have two possibilities. Let's say that we chose to write it to the left. Okay, so now for the third object, we have 3 relative locations. We can put it to the left of the second element, between the first 2 elements, or to the right of the first element. So we have 3 locations, and let's say we put it to the right of the first element. So we have these locations. Now for the fourth element, we'll have 4 locations to put it, either here, 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 or here, and so on. So until we get to the nth element, we'll have 1 possibility for the first location, times 2 for the second one, for the first smallest element, times 2 for the next smallest, 3, and so on up to n, or we'll get n factorial. So this gives us an alternative way of understanding how we get n factorial, which is in some sense a little nicer, because instead of going from n down, we're going from 1 all the way up to n. All right. Either definition, and maybe even more closely the second definition, leads us to a recursive definition of n factorial, which is as follows. So n factorial is n times n minus 1 and so on up to 2 times 1, or if you want, you can write it as we saw, 1 up to n up to n. And either way you do it, it's going to be n times the product of the first n minus 1 elements. So it's n times n minus 1 factorial. Okay. And this is true for all n which is bigger than or equal to 1. So in other words, it also holds for 1, and namely 1 factorial is going to be 1 times 0 factorial, and that's because 0 factorial was defined to be 1, and you can actually even extend it beyond 1 to negative values, right? So we can see this recursion here. So for 0, we get that n factorial is 1, and it's just 1 here. And if you want to get to 1 factorial, you multiply 1 by 1. If you want to get 2 factorial, you multiply 2. 3 factorial, you multiply 2 factorial by 3. And to get 4 factorial, you take 3 factorial, which is 6, multiply by 4, by 5, by 6, and so on. Okay. Now, what we want to do next is go over several applications of this formula and count a number of basic permutations and do several examples of permutations. So first of all, suppose you're planning a trip to 3 cities, and you wonder how many ways you can arrange your trips, in how many different orders can you visit those cities. Let's say Los Angeles, San Diego, and San Francisco. So you can go Los Angeles, San Diego, and San Francisco, or you can go San Francisco, San Diego, Los Angeles, and so on. So how many ways can you arrange your trip? So clearly there is going to be 3 factorial, because there are 3 factorial ways of arranging those objects, which is 3 times 2 times 1, which is 6. Okay. Now, another application, basic application of permutation, is an anagram of a word is a rearrangement of the letters. So the question is, how many anagrams does a word with 5 distinct letters have? So for example, if we take pears, then it has spear, and which is a word, or EARPS. Those the same letters rearranged, and we're not insisting that will be an actual English word. So how many anagrams or how many permutations do those 5 letters have? Then again, looking at how many permutations do 5 objects have, and that's, as we know, is 5 factorial, and we 5 times 4 times 3 times 2 times 1, which is 120. Right. Now, we can look at constrained anagrams of, for example, pairs. So what if the letters A and R must stay adjacent, like they are originally, and furthermore in order, namely A followed by R? So for example, we're counting words like parse, A followed by immediately by R, or separ, SEPAR, which is not a word, but it's a sequence of these 5 letters where A is followed immediately by R. So if we would like to count how many such anagrams there are, then one could observe that what we're looking at are permutations of P, E, and then AR combined and S. So for example, parse is P followed by AR, followed by S, and followed by E, and separ is SE, followed S, then E, then P, and then AR. So the number of such permutations is, we have 4 objects, and the number is 4 factorial, which is 4 times 3 times 2 times 1, which is 24. Okay. Now, if we would like to count the number of anagrams where AR are adjacent, but they can appear in any order, namely AR or RA, then we're counting things like spare, AR adjacent, A comes before R, or RAESP, where A and R are adjacent, but R comes before A. And now we notice that there are 2 ways to order those letters, AR or RA. And for each order, as we've seen before, there are going to be 24 ways. So the total number by the product rule is 2 times 24, which is 48. Because these 2 types of anagrams are disjoint, are distinct. Those that have AR and those that have RA are different, so they add up, and by the multiplication rule, we get 2 times 24, which is 48. Okay. Now, what if we wanted anagrams where A and R are not adjacent? Then, for example, AESPR and SRPAE, then we can note that what we could do is we could look at all possible anagrams of pairs, which in the previous slide we calculated to be 120, and we can look at we can consider all anagrams where A and R are adjacent and in any order, which here we calculate to be 48, and we can just look at the complement of this set relative to all possible permutations, and then by the subtraction rule we get that the total number of permutations or anagrams where n are not adjacent is 5 factorial, which is the total number of permutations minus 48, so 120 minus 48, namely 72. Okay, now let's look at more additional constraint permutations. So how many ways can you organize 3 distinct boys and 2 distinct girls in a row or in a line? So if there are no constraints, then you have these 5 kids, 3 boys and 2 girls, and you can organize them any way you want. So together we have 5 kids, and we want to arrange them. So there are 3 plus 2 factorial or 5 factorial, or 120 ways. Now, what if you want the boys and girls to alternate? Then necessarily you have to have boy, girl, boy, girl, boy. Right, so this is the arrangement, and now you can arrange the boys any way you want, and you can arrange the girls any way you want. So the boys you can arrange in 3 factorials and the girls in 2 factorial ways, and then any combination is possible. So again, by the product rule, we'll get 3 factorial times 2 factorial, which is 6 times 2, which is 12. A lot less than this permutation because we insisted on arrangement of boy, girl, and this is very restrictive. How about boys together and girls together? For example, here, 3 boys followed by 2 girls, or you could have 2 girls, the 2 girls followed by the 3 boys. So now we have 2 ways to arrange to decide if the boys comes first or the girl come first, and then we have 3 factorial ways to arrange the boys and 2 factorial ways to arrange the girls, and we get what the number we got before times 2, namely 24. Okay, and what if the boys and girls are unconstrained again, as they were here at the beginning, but the orientation, namely left to right or right to left, does not matter. Namely, if we have the same arrangement if an arrangement where this boy is here on the left and so on, we count it as the same as the arrangement where they're organized in the reverse way, then the number is going to be 120, or 5 factorial divided by 2, which is 60. Right? Now, you can also arrange objects in a circle, as we have seen in the title's picture for this talk. And so, for example, if we ask how many ways can you arrange 5 people at a round table, then you need to specify whether rotation matter or not. So, for example, here we have A, B, C, D, E, like 5 people named, say, A, B, C, D, and they're sitting in this arrangement. And here's another arrangement, again, A, B, C, D arranged if you go counterclockwise, but these 2 are different in the sense that we just shifted everyone by 2. So it's the same arrangement where B follows A and C follows B in both of them, but they're shifted by 2 here. This one we just cyclically shifted to the left twice. So you need to decide whether these 2 you consider to be the same arrangement. In these 2, everyone sits next to the same people on the left and the right, but do you consider them different? If you consider them different, these 2 arrangements, then we're back to counting things on a line, because you have 5 possibilities to put here, times 4, times 3, times 2, times 1. So you'll get 5 factorial or 120. On the other hand, if you don't care about rotations, you only care about the relative sitting of the people, then you consider these 2 arrangements to be the same. And in that case, you can see that every 5 permutations that you get here, you'll consider to be identical. So the total number is going to be 5 factorial divided by 5, namely 4 factorial, or 24. Okay, so hopefully this gives you some idea about different applications of permutations. And I want to just end by talking about n factorial and how it grows. So here's a table that shows n factorial for n going from 1 up to 20. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, and then 24, 120, and 720. And as you can see, these numbers grow quite fast. And the reason they grow quite fast is because they actually grow faster than an exponential, because exponential is 2 times 2 times 2, and these are 2, it grows as 1 times 2 times 3, and you keep increasing. Okay, luckily, there's a way to approximate this growth. They call Stirling's approximation, or Stirling's formula. And it says that n factorial grows, while it will grow faster than exponential, faster than 2 to the n or e to the n, but less than n to the n, as we can see, because it's 1 times 2 up to n, all the terms are less than n. But more precisely, it grows roughly as n over e to the n. And even more precisely, it grows like n over e to the n times square root of 2 pi n. Okay. And this approximation is quite good. For example, if you look here, if you look at n equals to 10, then here is n factorial, and here is Stirling's approximation. And you can see Stirling's approximation is off by 0.0002 or 0.0003%. So already for n equals to 10, it's actually very, very accurate. Okay, and here is a graph that shows n factorial relative to its Stirling approximation, and as you can see here, the graph already for maybe even 3, if you look at this table, if you look here, looks pretty much the same. So this is a very good approximation. And in the Python notebooks for this class, you can actually calculate. We have created functions that calculate Stirling's approximation and factorial, and you can play with them and see how good the approximation is. Right. So so far we have talked about permutations of objects, and we talked about n factorial. And what we would like to do in the next lecture is talk about partial permutations. See you then.